Section 2.7, rates of change in the natural and social sciences. So they're just going to give you some word problems in either the natural or the social sciences. So on page 178, problem 14, a stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Find the rate at which the area within the circle is increasing after A, 1 second, B, 3 seconds, and C, 5 seconds. What can you conclude? So after you've done that, maybe you can figure out some sort of pattern that's occurring. So let's do this. So part A. Actually, this part A is going to be applicable for all the other parts. So first, we drop this little pebble into this pond. So I have a pond here, and I drop a pebble into, or a stone into this lake, and the ripples go out in some circular pattern. So the question is, well, what's the equation for a circle? Okay, so you have here some circular pattern. Okay. And so the equation, and you want to find, well, now the question is, well, what do you want to find? It turns out that I know the speed at which these ripples are traveling. So this ripple here is traveling at some particular speed, 60 centimeters a second. So it's going 60 centimeters a second. Okay. What do you want to find? I want to find the rate at which the area. So the rate of the area. So I want to figure out how fast is this area going. So I have to figure out a formula for the area. So let this R be the radius of your circle, the area of a circle of radius R is pi R squared. I know the following, that each of these radiuses, this is going out at this speed. Therefore, if I travel along this radius, it's going out at a speed of 60 centimeters per second. Okay. Now, I want to determine the derivative, the rate at which the area is changing with respect to what variable? Time. So if you look here, it's implicit. They don't tell you. Here, they don't tell you. It says rate. Okay, the rate is derivative. I know that. And it says derivative of what? Area. But the question is, what's with respect to what variable? With respect to the radius or with respect to the time? It's implicit that when I say a rate isn't, that if you look at this situation, when I talk about rate, I'm measuring how big it's getting with respect to time. And so this is dA dt. I want to figure that out. When? Well, in part A, when t is equal to 1 second. This will be, since the radius is given in centimeters and the time is given in seconds, this rate will be given in square centimeters per second. Okay, I can get rid of this drawing. This is just meant to help. That was just sort of a helping drawing. Okay, so once you've done this, you're really almost done. So I have here a formula, and I have these quantities here. I want to figure out this, so take the derivative. And we can take the derivative using the chain rule, using implicit differentiation. And so I have here that A is pi r squared. So let's take the derivative of this respect to t. And so I have that dA over dt is equal to, bring down the 2 out in front, rewrite what's inside, all times the derivative of what's inside. And now let's plug in what we know. So we know that the radius, oh, I guess we don't know the radius. Oh, we have to figure out the radius. Yeah, okay, so now you're sort of stuck because now you've got to plug in r. I don't know r. So let me try to figure out what r is. I know dr dt. Dr dt is this. So I have to figure out what. So I know this. Obviously, I know 2 pi, but I don't know r as a function of t. One thing to notice is that, oh, I got rid of my little drawing. Here's your pond. Here are your ripples. Well, one thing I know is before the stone here hits the water, there's no ripple. Therefore, the radius of the ripple is going to be 0 when the time is 0. So time t equaling 0 means that that's the instant that the stone hits the water. Well, at the very instant it hits the water, you don't have a ripple yet, because it's just, it's one molecule is touching another molecule. It hasn't really had time to propagate this energy. So I know that initially its radius, the radius of this ripple is 0 centimeters. So now I want to figure out, well, after 1 second, how far has it gone? Well, I know the following. I know that it travels at this constant rate of 60 centimeters a second. So after 1 second, it's gone 60, it's gone 60, this wave has gone 60 centimeters. So the radius of this circle is going to be 60. Okay, good. So therefore, now I can plug in. So dA over dt equals 2 pi r dr dt. the radius r is 60. The rate of change, dr dt, is 60 centimeters per second. Therefore, 36,7,200 pi square centimeters per second. And that is the rate at which your area is changing. Any questions about that? Okay, let's do part B. Well, for part B, I want to figure out what happens after 3 seconds. Just like before, the radius of your ripple, your circle, is going to be 0 when t is 0, after 0 seconds. After 3 seconds, since it's traveling at 60 centimeters a second, it should equal 180 centimeters. Therefore, dA dt, which is 2 pi r dr dt, should equal 2 pi times 180 times 60. And so that's going to equal, that's a 216. 21,600 pi square centimeters per second. So that's the rate at which this circle is increasing. Let's look at what happens after 5 seconds. Okay, so originally its radius is 0. After 5 seconds, since it is increasing by the rate of 60 centimeters a second, after 5 seconds, it's the size of 300. And so dA over dt is equal to 2 pi r dr dt which is 2 times pi times 300 times 60, which is 3,600. Oh, the 3 zeros, 36,000 pi square centimeters per second. Okay. So now any questions about that so far? So now what you should notice is for part A, so at 1 second, so maybe I'll write it this way. So dA dt after 1 second was 7,200 pi. After 3 seconds, well, it's 216,000 pi. And so this is actually, that's times 1. If I multiply 7,200 times 3, I get the 21,600 pi. And lastly, if I multiply 7,200 pi times 5, I get 360, so that's 36,000 pi. So what this says, is that the rate of change in the area of the ripple is linear is a linear function, well, is linear in time. That the rate of change is just 7,200 pi times t, square centimeters per second. And so that's the, that's how the area increases. Any questions about that? Okay. Oh, good. Problem 36. In a fish farm, a population of fish is introduced into a pond and harvested regularly. A model for the rate of change of the fish population is given by the equation dp dt is equal to r sub 0 times 1 minus p at t divided by p sub c times the quantity p of t minus beta times p of t, where r sub 0 is the birth rate of the fish, p sub c is the maximum capacity, is the maximum population that the pond can sustain, called the carrying capacity, and beta is the percentage of the population that is harvested. A, what value of dp dt corresponds to a stable population? B, if the population can sustain 10,000 fish, the birth rate is 5% and the harvesting rate is 4%. Find the stable population level. C, what happens if beta is raised to 5%? Okay, so let's do this. So for part A, it says that you want to determine the value of dp dt so that we have a stable population. Well, if you want your population to be stable, you don't want the population to grow, nor do you want the population to decrease. And so you do not want any change in the population. So you want some sort of stable population. So you want that the population should not increase, nor should it decrease. You want it to be stable. You don't want the population to rise or to fall. You want that the rate of change in the population is 0. And so we want that dp dt is 0. Let's do part B. So for part B, we're given some, population of fish, their birth rate, harvesting rate. You want to figure out the stable population level. Okay, so let's figure out the stable population level. Given the following facts. So we're given that we want to sustain 10,000 fish, meaning that we want a carrying capacity of 10,000 fish. So I want my carrying capacity to be 10,000. Next, I want that I'm given that my birth rate is 5%. Per year. So 0.05 per year. Next, I'm given that here it is, that my harvesting rate, beta, is 4%. So I'm given that the harvesting rate is 4%. So 0.04. And so I want to figure out my stable population, meaning I want that this is 0, meaning I want this is 0. So let me write, well, actually, maybe I'll write this whole thing down. So I have that dp dt is equal to R0, 1 minus p sub t over p sub c times p of t minus beta p of t. And since it's a stable population, I also have that dp dt is 0. And so, actually, maybe I will maybe I won't actually plug in the numbers yet. Let me not plug in the numbers yet. So I have R, because if plugging in these numbers, you're going to get really weird looking numbers. So maybe I'm not going to plug in those numbers at this moment. I will in like a minute. So I have R0, 1 minus P of T, P sub C, P of T minus beta P of t is 0. So let me factor out P of t. First off, I don't want P of t to equal 0. So if P of t equals 0, then I'm not really, so this implies that R0, 1 minus P of t over P0 minus beta is 0, or P of t is 0. Well, if P of t is 0, that means that your fish is the number of fish that you have is always equal to 0. And so it means that you've killed off all your fish. And so I don't want to kill off. I don't want, in other words, if you start with no fish, then you have no fish at the end. Let me assume that I have some fish at the beginning. So let me assume that P of t is not 0 for all t. So let me assume I have at least one fish in the pond. So then P of t is not going to be 0 for all time. So that at least there's something in the pond for some amount of time. So now let's try to figure out what P of t is. So let's bring beta to the other side of my equation. So R sub 0 times 1 minus P of t over P sub 0, P sub c. Why did that become a 0? Don't know. The carrying capacity, P sub c, is equal to beta. So I have that 1 minus P sub t over P sub c is equal to beta over R sub 0. I'm assuming, of course, R sub 0 is not a 0. And so I have that P t over P sub c is equal to 1 plus beta over R sub 0. Why do I, yeah, no, R sub 0 is correct, okay. Okay, so let's multiply both sides of my equation by P sub c. And so I have that P of t is equal to P c, the carrying capacity, times 1 plus beta over R sub 0. Okay, so let's plug in. So let's plug these numbers in to see what I get. And so P sub t. So that's going to be the stable, our stable population. So I don't want my, as I said, I don't want my stable population to be 0. I don't want to kill off all my fish. So this is going to equal P sub c. Well, my carrying capacity was 10,000. Beta, the harvesting rate was 4%. R sub 0, your birth rate was 5%. Four divided by 5 is 0.16. No, That's 0.18, 0.8. And so you get 18,000 fish. So this means that you start with 10,000 fish. Since you're harvesting a few of them, less than how many are being born, then you're going to increase the number of fish, but eventually they're not going to increase past 18,000. So they're going to start at 10,000 and slowly increase until there are 18,000 fish. Okay, let me do part C. So, but what happens if you raise it to 5%? Oh, okay, so part C. Well, I noticed, actually, I've already solved. So I've already solved this equation in general. So I have that P of T is either 0 or equal to this. So let's figure out what this is. So you start out with 10,000 fish. You then wait 1 second. When I bring this to the other side of my equation, this becomes negative. That's positive, but this is negative. Wait 1 second. Wait 1 second. That was error. Okay, made a mathematical error. So that is 1 minus 0.8 is 0.2 times 10,000 is 2,000. Sorry about that. There was an error, a sign error. So if you start with 10,000 fish and you have a birth rate of 5% and you harvest at a rate of 4%, then they decrease down to a size of 2,000 fish. So I guess since you're killing off a lot of them, you only have at the end 2,000 fish, and that it stabilizes at 2,000. Now, suppose that your harvesting rate is 5%, and your birth rate is also 5%. So those cancel and you get 1. 1 minus 1 is 0. So the answer is you've killed off every fish. And so if you start out with 10,000 fish and your harvesting rate is 5%, and the rate at which the fish